Good morning, everyone. My name is Allison Reyes Gutierrez, and today I will be discussing the synthesis of methyl orange via a diazonium coupling reaction, an experiment conducted under Dr. Hyatt's guidance for the Organic Chemistry 2 lab. The azo dye methyl orange was synthesized using sulfonilic acid and N-dimethyl aniline. The product was analyzed using UV-Vis light spectroscopy on the acidic and basic samples. The percent yield was also calculated for a quantitative analysis. For future experiments in the crystallization part, it is recommended to heat the methyl orange solution to boiling in order to maximize the quantity of crystals formed. Methyl orange is an azo dye, which is a dyeing agent containing an azo group or a nitrogen atom double bonded to another nitrogen atom. As you can see in figure 1, this is the azo group of methyl orange. Methyl orange is also used as a pH acid-base indicator due to its color change to red in its acidic form and a color change to yellow in its basic anion form. The diazonium coupling reaction consists of an electrophilic aromatic diazonium salt, which is then reacted with a nucleophilic aromatic molecule, which is our N-dimethyl aniline. Azo-coupling reactions also tend to react in the para position due to a steric hindrance from the bulky aromatic molecules. Figure 1 shows a reaction of sulfonilic acid with sodium bicarbonate forming 4-aminobenzene sulfonate, which is then reacted with HCl and NaNO2 to give the nitroso ion, which then attaches to the sulfonilic acid and replaces the amine group with a nitrogen triple bonded to another nitrogen. This is then reacted with a nucleophile, which is the N-dimethyl aniline, where hydrogen in the benzene molecule is substituted for a carbon-nitrogen molecule, thus resulting in the formation of methyl orange. Azo dyes can also absorb wavelengths found in the visible light spectra when their electrons get excited and jump up to a higher energy orbital than the one it usually occupies. When a certain wavelength is absorbed, the complementary color is observed. For example, in figure 2, if a dye absorbs a wavelength of 500 nanometers corresponding to green, the actual color visible to the human eye is going to be red, not green, which is the complementary color of green. Sulfonilic acid was added to sodium bicarbonate until the solution tested basic. Then sodium nitrate was added and the solution was heated gently, cooled, then placed in an ice bath with hydrogen chloride was added dropwise. A mixture of glacial acetic acid and N-dimethyl aniline, which formed the nucleophilic aromatic molecule, was added to the solution, along with sodium hydroxide and allowed to crystallize. The product was collected under vacuum filtration and further dried in the oven. The weight of the product was determined, and a small amount of product was combined with deionized water and divided into 2 cuvettes where hydrogen chloride and sodium chloride were added to collect UV-Vis spectra. The limited reagent was sulfonilic acid, and her theoretical yield was 0.945 grams, and her actual yield was 0.678 grams, accounting for a total percent yield of 72%. During the procedure, after the addition of the N-dimethyl aniline, a brown-purple paste was formed, as shown here. After 10% sodium hydroxide was added, the solution turned bright orange, as shown in figure 4. During the pH test, addition of 5% hydrogen chloride resulted in a color change to bright red, shown in figure 5. An addition of 5% sodium hydroxide resulted in a color change to bright orange, shown in figure 6. The lambda max of the acid was measured to be 503.6 nanometers compared to a literature value of 506 nanometers, and the basic lambda max was recorded at 447.9 nanometers compared to a literature value of 462. The results of the pH test indicate that methyl orange was successfully synthesized. The acidic sample absorbed green wavelengths and reflected its red complementary color, as discussed earlier. The basic sample absorbed blue wavelengths, reflecting the orange complementary color. similar to the expected yellow hue. The low percent yield can be attributed to the failure to heat the methyl orange solution to boiling as recommended by the procedure. The solution was instead heated gently to about 40 degrees Celsius. The failure to completely dissolve the solution resulted in a low crystal yield and thus a decreased amount of methyl orange formed. It can be concluded that proper crystallization of the methyl orange solution is a key step for accurate synthesis of methyl orange. During the crystallization of methyl orange, the solution must be heated to boiling to increase the amount of methyl orange crystals to be recovered via vacuum filtration. It is recommended to follow procedure instructions carefully in order to maximize the percent yield of product synthesized. Thank you for watching.